Hello students. Today we will discuss about Josephson junctions. So I assume that you have seen my previous lecture on superconductivity. And if you have, and although you have not seen, I believe that you have some knowledge of superconductors. Now, Josephson junction is actually a thin layer of insulator sandwiched between two superconductors. So it's a thin layer. So actually, it's not a thin layer, but when a thin layer of insulating material is sandwiched between two superconductors, then two Josephson junctions are formed. Now, for a thick insulator, the electrons cannot get through the superconducting layer, get through the insulating layer from one superconductor to another superconductor. So this is one superconductor, and this is another superconductor, and we have created a insulator. So this has to be very thin, of the order of few nanometers. So if it is thick, the electrons won't be able to pass from one side of the superconductor to another side. It has to be thin. Now for the thin layers, now the electrons that we assume are passing are actually not a single electron but a pair of electrons, and they are called Cooper pairs, and they are basically bosons having integral one table of spins. A single electron is a fermion, but these are bosons. Now, as these bosons pass through, the tunnel current can be written as J is equal to J0 sine delta, where J0 is the maximum supercurrent density through the insulator with zero potential difference across it, and this delta is the charge, is the change in phase of the order parameter of the Cooper pair across the junction. So let us write it once again. J is equal to J0 sine delta. This is the maximum supercurrent density, and this is the phase change. Now we assume here that there is no potential difference applied. Then we are getting a current density like this. Now, if a potential is applied, now isn't so in presence of a DC voltage, across the insulator, the current density becomes J is equal to J0 sine delta plus Q by H cross Vt, where Q is of course the charge of the Cooper pair, that is 2 electron. Now this equation. Now let us write the equation once again. J is equal to J0 sine delta plus Q by H cross V into T. Now for ordinary voltages, QV by H cross gives a very high frequency, so that the sine function oscillates rapidly, yielding a zero average value. Okay, so for this gives a very high frequency, so it averages out to be equal to 0. Thus we obtain current for no applied voltage and no current for an applied voltage. Now for an this is for an AC Joseph. So the oscillations that are, although there are oscillations due to this sinusoidal nature of the current, these oscillations, they average out to be 0 when we are applying a DC voltage across it. Now what happens in an AC Josephson effect? So this is actually the DC Josephson effect. Now coming to the AC Josephson effect, instead of applying a DC voltage, we applied an AC voltage, that is we applied Vt is equal to V0 plus Vd cos omega t. This is the AC voltage applied. Well, this is the DC voltage that has been applied, and Vd is much less than V0. So very small amount of oscillating voltage has been applied, amplitude. So if we put these V here, the equation will turn out to be like this. So now J becomes J0 sine delta plus Q by H cross Vt plus G0. So again you have Q by H cross Vt by omega into you have sine omega t and to cos delta plus Q by V0 t. Now in DC case, for ordinary voltages, the first part averages to be 0, as we have seen in the earlier case. For ordinary voltage, this part will average out to be equal to 0. The second part also yields a 0 average value, except for a very special case. The second part will be also equal to 0, except for a very special case. To find the special case, we need to expand the second part. So writing the second part once again, the second part is J is equal to J0 Q by H cross Vd by W, and we have sine, so we are expanding the, so let's write once again, it's sine omega t into cos delta plus Q by H cross V0 t. So expand it in terms of cos A plus B. So it's cos A plus B E is actually equal to cos A cos B minus sin A sin B. So the term J is equal to J0 Q by H plus UD by omega. This remains the same. This remains the same, and we have just 1 second. We have sin omega t into, use a different color here, so the cos delta cos q by h cross u0 t minus sin delta into sin q by h cross u0 t. Now if so this term will also be equal to 0 unless and until we have omega is equal to q v0 by h plus. So only then we can have so this becomes q v0 by h plus. This becomes omega t. So we get a term sin square omega t becomes sin square omega t. If q is equal to v0 by h cross. So we can see that with omega is equal to q v0 by h cross, a current is observed to be flowing through the conductor. This phenomenon is analogous to resonance and has been experimentally verified. Now since q is equal to 2E, q is equal to the AC Josephson effect can be used to measure the fundamental constant E by H. So it becomes 2E V0 by H cross. It could be so AC Josephson effect can be used to form fundamental constant E by H cross very precisely, and also is a technique for measuring the voltage very accurately. So the very accurate voltage determination can be done with this AC Josephson effect. Now the tunneling current now is quite sensitive on the magnetic field applied at the junction. So in a Josephson junction, if you are applying a magnetic field, so then the tunneling current is very sensitive to that. The tunneling current is expressed at I is equal to I0 sin pi by pi 0 divided by pi by pi 0, where I is dependent on the temperature and the structure of the junction. Phi is the magnetic flux. So this pi, this is the magnetic flux, and phi is the flux quantum. This is the flux quantum. So we can see that the tunnel current actually varies like this. Apply the magnetic field in this direction, and we observe the current in this direction. So it will take a shape like this. Okay. And now the interesting thing occurs when we are using a circuit called SQUID. SQUID stands for superconducting quantum interference device. So the construction of the SQUID is like this. We have two two Josephson junctions formed in this way. So there are two Josephson junctions. There are two insulators, and there are two currents. We will have two currents. This is I1 and this is I2. These two currents pass through the superconductor, tunneling through the superconductor, and then again interfere. So I1 and I2, after tunneling, interfere with each other. This is what happens for SQUID. Now, the magnetic field is applied through the central region. So, central region, we have a magnetic field applied, phi, and the current in the two paths, I1 and I2, combine to give the total current through the junction. Okay, so if we look at the total current per interference, it comes up to be I is equal to I0 sine phi 0 into cos 3 phi by h. Now phi 0 is a constant and phi is the magnetic flux, we have already seen. Now this current is oscillating function of the flux. So we can see that the current is an oscillating function of the magnetic flux. Flux stands for number of lines, magnetic lines per unit area, and the current attains a maximum. This current will attain a maximum when E phi by h cross, it is an integral multiple of phi. When it's integral multiple of phi, it will attain I will be maximum. So from here we can find that we can actually find the value of the flux quantum. So the flux quantum is given as phi O is equal to phi h cross by E. This is 1 is the flux quantum, taking S is equal to 1. This is an integer. The flux quantum So the oscillations originate from the interference of the currents. So as we have seen, there are two currents, I1 and I2. So when they interfere after passing through the superconducting junctions, they form the current I, and also it undergoes oscillations. So this is all about SQUID, and SQUID is a very precise device, a very efficient device. It can measure up to 10 to the power minus 18 Tesla of magnetic field. So this is very highly precise measurement of magnetic field. This is called Atto Tesla, ATTO. Right. Echo means 10 to the power minus 12. M2 stands for 10 to the power minus 15, and Atto stands for 10 to the power minus 18. More than that, there is nano, 10 to the power of minus 9, micro, 10 to the power of minus 6, milli, 10 to the power of minus 3, deci, 10 to the power of minus 1. If you go to the above terms, we have kilo, 10 to the power of 3, mega, 10 to the power of 6, giga, 10 to the power of 9. Okay, so this is the distribution. So in SQUID we are getting 10 to the power minus 18. This is up to date. It is the most precise. There is no instrument which can go beyond this type of SQUID, and it is used in getting that image plot, the hysteresis plot that you obtain for magnetic materials versus H. SQUID is very much used in that.